So, in the last class we discussed the concept of the center of mass that is associated with the system of particles and rigid bodies, and we had also seen a few illustrations and examples as to how to calculate this center of mass. Some of the problems were straightforward, and a particular problem where there was a continuous mass distribution was involved, we had to make use of an integration. And so, please do not be scared of using mathematical techniques while solving physical problems. Before we move on to today's topic, it is very instructive to work out a problem which was discussed in the last class, which was sort of left in the middle. This problem is like this. So, we had 4 masses, which were distributed along the vertices, at the vertices sorry of a square. This is x axis, this is y axis, and here it is 1 kilo, the vertex is minus 1 comma 1, and this here it is 2 kilos at this point, at this vertex, and this is 1 1, and here it is again 1 kilo, and its vertex is x1 and y minus 1, and at this vertex it is 2 kilograms and it is minus 1 comma minus 1. This problem we did. So, just for the sake of what I can say recalling, remember when I write a coordinate as 1 comma 1, this actually means a vector 1 times I plus 1 times j, which is this is same as I plus j, and sometimes unit vectors are also denoted as in this way. I is denoted as Ex times 1 plus 1 times unit vector along y direction, therefore Ex plus Ey. See, both are same. So, when you see a different notation, you should not get confused, both these notations are used. We did this problem and then we got the center of mass as or center of mass as 0 comma 0, that means it is at the origin. This problem was, after that we changed the problem. The changed problem is like this. Suppose it is a lamina, this is the second one, where the 2 kilogram, this portion has 2 kilograms as weight, and this portion has 1 kilogram as weight, but it is a lamina of uniform thickness. Okay, this is 2 kilograms, this is 1 kilogram, this is 1 kilogram. So, we want to calculate the center of mass of this system. Remember, the center of mass of this is, so it is 2 kilograms. The center of mass of this lamina portion, remember it is a uniform lamina. So, by symmetry considerations and geometry, the center of mass would be located here. What are the coordinates? Drop the x axis half and y coordinate is going to be this half, right. Similarly, the center of mass of this system would be, from here it is half, and if I drop here it will be minus half, right. So, let me write here it is 2 kilograms. So, the center of mass of this is minus half comma minus half, this is 1 kilogram mass lamina, the center of mass would be minus half comma half. So, you can check up whether you have done the calculations correctly. Now, the center of mass of this system is equal to, So, this whole mass is represented by this particular point, that is where this 2 kilograms is concentrated. So, it will be 2 into half comma half, right, plus we come here, it is 1 kilogram into, it is located at this particular vector, plus here it is 2 kilograms, 2 into minus half comma minus half plus 1 kilogram, sorry, it is 1 kilogram, which is placed at the center of this squarish lamina, right. That is what the center of mass of each of this. Okay, this whole thing divided by mass, this is 136 kilograms. Now you can see that what is going to happen, this is half, this is minus half, plus half, minus half. Similarly, half minus half will cancel, and then you have minus half with plus half. Therefore, this is again you get the answer as the origin. Okay, origin is the center of mass. See, please do not be under impression, in any problem where you are required to calculate center of mass, it is going to be the origin. Okay, I have chosen it for the sake of convenience. So, for example, if I am going to have 1 kilogram here and then 2 kilogram here, obviously you will see that with respect to the mass distribution, there is less mass on this portion, 1 plus 1 2 kilograms. On this side there is more mass, it is 4 kilograms. Obviously, when you calculate, the center of mass of the system will shift from the origin to the right hand. Okay. So, that you need to be careful. Now, we will move on to the today's portion. After having introduced the concept of center of mass yesterday, now we have to move on to other topics like what about the motion of center of mass, how does it move? This is something similar to the one dimensional problems and two dimensional problems which we had discussed earlier on a motion on a plane. That is one thing, and important concepts like linear momentum, momentum conservation, etc., we have to deal. So, you can see that there is with respect to the development of the subject, there are close parallels between what you have studied in kinematics in 1 and 2 dimensions and now, and right, and now we shall proceed to study the such systems. So, just for the sake of convenience, we will write the center of mass of a system. You have particles m1 at r1, and this is another mass m2 which is at a position at a r2, etc., and then I have here rn, this is mn. Then the center of mass of the system is given by, which we had seen. If you want to write this is RCM also you can write, just for our reference, is equal to, what is that do? So, each mass is multiplied by its corresponding position vector and this summation by mi, I running from 1 to n. Here since we have little n number of particles, and okay. So, this is same as if total mass is m, I running from 1 to little n, mi ri divided by capital M, where I can say that m1 plus m2 mn is capital M, is total mass of the system of particles. So, so what do we do? This we can write it as, I can bring the m to this side, I have m times r is equal to m1 r1 plus m2 r2 vector r2 rather plus m sub n times rn vector. Now, what I do, I differentiate on both. This looks like a momentum conservation, this is what some of the momenta of all the particles. So, each momenta is being multiplied by, and this is nothing but this also represents the momentum of center of mass, of total mass m rather. Okay. Now, I will differentiate on both sides with respect to time. Let us remember that the masses are not changing in time, and so masses are all constants in time, constant masses, and therefore differentiate with respect to time on both sides. Remember, the particles are going to move, masses are not going to change, therefore the position vectors of these particles are all functions of time. Therefore, there is meaning in talking about differentiating the positions vector with the position vectors with respect to time. So, what do we get? M into dr by dt is equal to m1 dr1 vector by dt plus m2 times dr2 vector by dt etc. all the way up to m sub n drn vector by dt. So, we know that what is this dr1 by dt is nothing but the velocity vector of the first particle. Similarly, this is this quantity dr2 by dt is the velocity vector of the second particle. Therefore, I can write m into velocity vector I will call by little v1 m1 plus m2 times v2 etc. plus m sub n vn. Now, this dr by dt I will call it as capital R, capital V, sorry. So, this is now what it means, this is the velocity of center of mass, the whole mass is all these masses are represented by capital M. Therefore, this V is the center of mass velocity. So, V is, we will write here, so here V is the velocity of center of mass. Okay. So, so velocity of the center of this is the expression for the velocity of center of mass. So, if you want we can bring this m here and have a nice expression, this is good enough. Now, what I will do, we will again differentiate this with respect to time, because velocities also keep changing. Therefore, m into, we will call this as okay, is equal to m1 a1 plus m2 a2 etc. plus mn an, where a is what? It is the acceleration of the center of mass, therefore it is dv by dt, and a sub n is the acceleration vector of the nth particle, therefore it is given by dvn by dt. So far so good. Of the ith particle I can do y only doing for the nth particle. Okay. Now, this is same as m into a is equal to, what is m1 into a1? That is the force, external force that is acting on the first particle, that is the exactly the force term which is responsible for causing an acceleration of a1 on the first particle. Therefore, it is f1 plus this is second is f2 force plus f sub n. So, what does it mean? The vector sum of forces acting on the particles is exactly equal to the mass of the system of particles multiplied by the acceleration of the center of mass. So, this is mass of the center of mass times the acceleration of center of mass is equal to all the external forces acting on the system. So this is, you call it as you call this term as force external, this you call this as force external. And so the center of mass of a system of particles moves as if the entire mass of the system is concentrated at the center of mass and all the forces were, all the external forces were applied at that particular point. So what you have is this situation, let us say that we have here a scenario, this is what we maybe I can use the same diagram, okay. So this is M1 here, M2 here, Mi here, etc., right. So external forces are acting on it, various external forces acting on is F1 here, this is F2 here. I am not denoting the actual force vectors. Now the whole picture can be replaced by the center of, let us say the center of mass of the system by a different colored chalk I have here. So this is the center of mass. So all these white dots can be sort of replaced by this M, and it is going to move with an acceleration A, I will denote it by A here. So all these particles and the external force acting on it can be replaced by simply this particular one, center of mass moving with an acceleration A. This is a very nice way of looking at things. And okay. Now this is the governing equation, rather M into A is equal to F external. We will explain in a moment what are the external forces. This is the sort of governing equation. This is the, what you call it as the governing equation for a system of particles. On one hand you have forces, external forces, each force will cause an acceleration. On the left hand side you have the whole scenario can be replaced by one mass, namely capital M, and it is moving with an acceleration capital A. And we have specifically used the term F sub external. What do you mean by external, sir? Forces are divided into, forces can be divided into, we will come over here. So right now the kind of problems we are dealing with where the forces are involved, they are divided into external forces external and another one is internal. What are external forces? For example, we have, let us say, several particles of masses M1, M2, etc., they are all falling under gravity. So gravity is the external force, it does not take into account the kind of interaction between the different particles. And again, suppose I have some charges, I place these charges in an electric field or a magnetic field. So these fields will in turn cause some forces, these forces will make these charges move in a particular way. This is external forces, right. You know that a charged particle moving in an electric and magnetic field, it is given by the so called the Lorentz force term. And so these are external forces. What are internal forces? Internal forces are something like tension in a string, compression, torsion, shear, and suppose I take in a gas, the van der Waals gas, etc., there is a kind of attraction or a repulsion at various orders of length. These are all internal forces. These internal forces largely they do not contribute for the dynamics of the system, rather they contribute for structure, how the whole system is going to look like, what kind of structure it will form. And so generally external forces are what one calls them as applied loads. This is a terminology which is generally used. And Now, we will move on to the next concept, the linear momentum of a system of particles, and right, momentum of a particle, linear momentum of a system of particles. Right. So, we know the basic definition of a momentum. If a particle is moving with a velocity v, then its momentum is given by m times v, and Newton's second law is stated in this very familiar form. The rate of change of momentum is what we call it as force, or the other way you want to write, force is defined as the rate of change of momentum. Okay. So, the linear momentum of a system of particles is already defined as capital P, which is same as m into v. Remember, this is the terminology, I guess we have used it here in this equation. In fact, this equation is momentum conservation, this equation represents the momentum conservation. Just for the sake of clarity, again I am writing, this is nothing but m1 v1 is p1 vector plus p2 vector plus pn vector, right. Okay. So, the total momentum of a system of particles is equal to the product of the total mass of the system and the velocity of center of mass. So, I had said it earlier, the picture of that n individual particles each with a particular mass moving can be replaced by the motion of the center of mass, and it has got a mass. The center of the mass of the center of mass is capital M, sum of all the masses, and right, and okay. Now, what happens if external force is 0? If there are no external forces. So, from this equation I can write, from this equation I can get dP by dt this is the so called equation of motion for the center of mass. Now, we can get very relevant and useful information from this. Suppose F external is 0, there are no external forces acting on the system, then what will happen? Then automatically dP by dt is equal to 0. This implies P is equal to some constant vector. So, this means what? This means that the linear momentum of the system remains the same. This means the linear momentum of the system of particles remains the same as time progresses. Okay, this is what you call it as linear momentum is a constant of motion. So, this implies for a system of particles which are not subjected to external forces, the center of mass moves such that the linear momentum capital P is a constant of motion. In a technical language you say that the capital P is conserved. It is a technical language, better you learn this, that means it remains the same. Okay. Now what happens this, now P is same as mass times V, therefore the velocity of the center of mass remains constant, this remains, that the velocity of center of mass remains constant. That means it is not going to change its direction because it is a vector quantity. This is true only if there are no external forces acting on the system. And we will consider an illustration of this particular one. Let me consider an illustration. You can treat this as illustration or a simple problem, whatever way. Let us say that a particle is moving along a straight line, it is capital A, as a mass, that is not important what we are trying to do here, it is moving along a straight line, there are no external forces, okay. Now due to some reason it explodes, it is something like a bomb or something, it explodes and it becomes two pieces, let us say. So one of the pieces goes like this, the other piece goes like this, let us say. Right. Now what can you say about the center of mass? Since external forces are 0, the velocity of center of mass remains constant, therefore it has to move along, the same straight line further. Where is going to be the center of mass? This has to be somewhere here, such that you can join, it has to be in a straight line, let us say. Okay. So if external forces are not there, then we can, if any such explosion happens, it can get split into Y2, it may be 3 or 4 or several particles, then we can say for sure that what is the direction of center of mass, and that will be same as the earlier one. Okay. Now we will work out a simple problem, you can treat it as an illustration, and before that we will make few comments. So when a system of particles is separated into a system of particles represented by the center of mass, we have the following scenario. So the motion of the various parts is such that it is separated into center of mass, and what about the motion of these particles? These particles B and C move with respect to the center of mass, I will just call this X center of mass. Let me repeat, forget about this portion what we have had. We have here now these two particle system B and C which are moving. Now the center of mass is somewhere here, it is located at this particular point. So the motion of B and C can be studied in such a way that the linear motion of center of mass and the motion of B and C with respect to the center of mass, this is what you call it as the motion of various parts of a system is, the technical language you use the word separated, that means it is split, is separated, you can use or split, is split into one, the motion of center of mass, and 2, motion about the center of mass, about the center of mass. Please notice the words which are being used. The whole motion of this system is separated into motion of center of mass plus the motion about the center of mass. Okay? This is the advantage of using this. Now, we can ask various questions. What about the total kinetic energy of this system, this two particle system, whenever what about the total kinetic energy of the several particle systems relative to the center of mass, okay? That we will calculate. I will consider a simple example. We will consider some more harder examples involving intricacies little later. And so, the question we have is, what about the total kinetic energy, what about the total kinetic energy of a two particle system what about the total kinetic energy of a two particle system relative to center of mass. This is an important question. Now, we will consider a situation. I have two particles, this m1 is the mass, second one m2, and its velocity is v1, this velocity of this is v2 with respect to a suitable coordinate system, let us say that. Then first thing is, what is the velocity of center of mass? Velocity of center of mass is, we know this definition, we have been using it again, m1 v1 plus m2 v2 divided by m1 plus m2. I do not need this any longer. Again have the same situation as there are no external forces, only this is a two particle system. So, as we had seen this problem yesterday, the simplest one is a two particle system. Let us work it out for this. What is the question we asked? It is, we need to calculate the total kinetic energy of this system with respect to the center of mass, right? And so, velocity of m1, with respect to center of mass. See, this is a notation you have to be very careful, velocity of 1 with respect to center of mass, okay. So, this is velocity of the first particle with respect to the center of mass. No, it is like a relative velocity, it is a relative velocity, it is nothing but by definition v1 minus velocity of center of mass. Velocity of center of mass, we have the standard notation. Right. This we can calculate, this is nothing but v1 vector minus m1 v1 plus m2 v2 divided by m1 plus m2. I can multiply on both sides, I will have, sorry, I do the simplification rather, not multiplication by both sides, v1 minus m1 v1 plus m2 v1 minus m2 v2 divided by, I will do this calculation of the first particle, second particle is simple, right. What all I have done is that multiplied this m1 plus m2 by v1, that is what m1 v1 plus m2 v1, and these two terms I will write as they are. So, these two terms will get cancelled, I will have m2 into V1 minus V2 by m1 plus m2. This is the V1 center of mass, velocity of the first particle relative to the center of mass. Okay. Now, you can write down what is the velocity of center of mass for the second particle, which I will write it here. Velocity of the center of mass relative to the velocity of the second particle related to the center of mass. Okay. This again I will do the same thing, instead I will write here V2 minus V center of mass, this is equal to V2 minus, again I will do this, m1 V1 plus m2 V2 divided by m1 plus m2, right. So, I know what I will get, V2 m2 is going to get cancelled with this, I will have m1 V2 minus V1, this divided by m1 plus m2. This is the velocity of the second particle with respect to the center of mass, right. So, you can see the symmetry, there was velocity of the first particle with respect to center of mass consulted m2 and then V1 minus V2. Here velocity of the second particle with respect to center of mass consults m1 here and then V2 minus V1, right. And okay. Now, what I need to do is I need to calculate the kinetic energy of I will use a notation, kinetic energy of the first particle relative to the center of mass. This straight line just says where I am calculating this quantity, kinetic energy of the first particle relative to the center of mass. This will be by definition will be half m1 into the square of that m2 V12. Incidentally, what is this quantity? The relative velocity of the first particle with respect to the second particle, that is what we denote by V12. What is V12? The relative velocity of the first particle with respect to the second particle, that is nothing but V1 minus V2. These are all fairly standard things. Similarly, this would be, what is this quantity? The quantity here, this will be V2 minus V1. These two are magnitude wise same, but they are in opposite directions. Okay, that divided by m1 plus m2 whole squared. So, I can do this calculation, what I will get, half of m1 then m2 squared then magnitude of V12 squared, that divided by m1 plus m2 the whole squared. Similarly, I can calculate the kinetic energy of the second mass relative to the center of mass. Okay. This is half of m2 m1 V21 by m1 plus m2 the whole squared. This would be half of m2 squared, sorry, m2 m1 squared. This will be, since it is a magnitude, I can write whichever way I want, either I can write V1 comma 2 or V2 comma 1 divided by m1 plus m2 the whole squared. Okay. Now, when now I want to calculate total kinetic mass of the system, I need some space, but I can't erase there, therefore so kinetic energy of the system that is both the particles, with respect to the center of mass is equal to, I need to add these terms, it is very easy here, half, I have m1 and m2, I can take out common and then mod v1 comma 2 whole squared, here I will have an m2, here I will have an additional m1 coming here, that divided by m1 plus m2 whole squared. So, one power will get cancelled, I will simply have kinetic energy of the system with respect to the center of mass is half of m1 m2 by m1 plus m2 times the relative velocity of one of them with respect to the other. This is a very important quantity. There is a very specific reason why I have chosen this particular illustration to be done. And you see that this particular quantity is what is known as reduced mass. Reduced mass of m1 and m2, this is denoted by mu generally, it is m1 m2 by m1 plus m2. It has the dimensions of mass very clear, because there is a m square here in the denominator m, therefore, the reduced mass has dimensions of mass. So, therefore, we see that the two particle system moves, this two particle system moves as if it has a reduced mass and its value is given by m1 multiplied by m2 divided by m1 plus 2. And what is the velocity with which this moves? This is the relative velocity with which it is moving. And okay. Now, this is about the kinetic energy of system. We will make some comments about the center of mass little later. I will erase this, this I will keep, other expressions I can do. Sir, does it represent the total kinetic energy of the system? No. Remember, once you are having the kinetic energy of this of these particles m1 and m2, then what about the velocity of the center of mass? So, that I need to take into account. Therefore, total kinetic energy of the system is equal to half of mu times V relative whole squared plus, we cannot afford to forget the center of mass that is somewhere sitting, Cm center of mass, that would be, what is the mass center of mass of center of mass? Capital M, m1 plus m2, then its velocity Cm squared, Cm, then I have to square this. Okay. So, therefore, I will have half of mu times V relative whole squared plus half of m1 plus m2, and we know what is the expression for center of mass. m1 is moving with the velocity v1 and m2 is moving with the velocity v2. Therefore, velocity of the center of mass is this quantity, and I want to calculate the total kinetic energy of this system. Okay, right, this is the total kinetic energy of the system. It looks little causing a fear, but there is nothing, it is a very straightforward expression. Okay, I have 10 minutes. This cut panikalam. Right. Now, what is that we have done? The whole motion we are considering as if this the motion of center of mass and then the relative motion part. So, this is the kinetic energy of the relative motion part, this is the kinetic energy of the center of mass, therefore, total energy should be this. Let us check up whether this is correct. What all things we need to do is substitute for in this particular expression, substitute for very relative, and then add those things, let us see what we get, right. We have the expressions and all here, therefore I need not have this. Okay. So, I am going to right hand, I will call this as right hand side, this is what I am going to calculate here. The right hand side expression is equal to half of reduced mass is m1 times m2 divided by m1 plus m2 into this is relative velocity is v1 minus v2 the whole squared, correct. So, this would be half of m1 m2 divided by m1 plus m2 multiplied by v1 square plus v2 squared minus 2 v1 dot v2. This dot is very important because these are two vectors, there is a dot product involved when you take a square, whereas here they become simply scalars, okay. Plus, oh sorry, this is one half of the expression, other half is this expression is what I have written, this expression I have to write, so that I will write it as plus half of m1 plus m2 times the quantity over there, in the denominator I will have m1 plus m2 the whole squared times I will have here m1 squared v1 squared plus m2 squared v2 squared plus 2 m1 m2, little bit of space adjustment on the board, v1 dotted with v2. Okay, so one term will disappear and this I will, oh sorry, let me not do it here, this will be plus half of this will disappear, I will have 1 over m1 plus m2 whole squared. There is a and I will have here m1 squared v1 squared plus m2 squared v2 squared plus 2 m1 m2 v1 dot v2. Now, I can add these things, take term by term, I will see that. Now, let us look at this term and then let us look at, so 2 is not there please because that is gone. I will have half m1 m2 by m1 plus m2 then v1 dot v2. Here I have again same m1 m2 times v1 dot v2 by m1 plus m2. Therefore, this term and this term they will cancel. So, remaining I need to add these two terms. I will have here yes half of m1 v1 squared plus half of m2 v2 squared. This is the total kinetic energy of the system. So, we have a 2 particle system which is moving with velocities v1 and v2, its total kinetic energy is, this is the kinetic energy total. If we are looking the same system with respect to the center of mass, then we need, then these 2 particles, then the reduced mass will have a kinetic energy. So, this 2 particle system has a total kinetic energy this much expression half m1 v1 squared plus half m2 v2 squared. The same thing can be viewed the center of in the center of mass language in the following way. What is it? It says that the reduced mass of the system namely m1 and m2, it has a velocity, that is v relative velocity, therefore the energy corresponding to this is this much, plus the center of mass always has this much, it will also have kinetic energy. You add these two things, you will exactly get to be the same. So you need to do a little bit of algebra in simplifying it, I hope I can leave it. So now we come to the we will do little more problems later. We have time? 50 minutes aayta? Okay. Yeah. Now we will make some comments about the center of mass. How is the center of mass of a system defined? Center of mass of a system is defined as m1 m2 by m1 plus m2. Now we invert it, so I will have 1 by m is equal to 1 by m1 plus 1 by m2. Okay. The center of mass is also, we call it as mu, better I always use this symbol. You know it, if you have a fraction equal to sum of two fractions, then what you can say from this, mu is certainly less than or equal to m1 and also mu is certainly less than or equal to m2. Okay. So the reduced mass is always less than or equal to mass of the each body. Let us write it here, the reduced mass of a system is always less than or equal to the mass of each body, equal to mass of each body. You will find that this particular technique is extensively used whenever we have multi-particles. In particular, the simplest multi-particle system is hydrogen atom, where the nucleus consists of a proton and you have an electron. This is a simple two body system, where this problem is studied using this particular techniques. In the coming class we will discuss maybe one or two additional illustrations and then move further, and we have to move on to other topics like torque, angular momentum conservation, etc. And I will stop at this stage.